Now we get to some properties of integrals. Okay, let's consider what an integral means and what it represents. And we've discussed it, or at least shown examples of it. But an integral is a fancy way of saying, hey, let's find the area. Let's find the area from -2 to 4 of this function. Let's find the area from -1 to 2 of this function. Let's find the area from A to A. What? You didn't travel anywhere. You didn't go anywhere. Okay, so if this problem, very first problem, was a rectangle that started at -2 and ended at -2, then you would probably look at it and say, well, first of all, that's no rectangle. And then if I said, what's the area? You'd say, it's a line. There is no area. And I would agree with you. So since you have essentially no width to your rectangle, if it would be like the first example, then the area is 0. Okay? Well, sometimes you compute things backwards, potentially, if these numbers are out of order, and they don't always have to be alphabetical, but for our purposes, we'll assume that A is less than B, just for the sake of this conversation. So if I'm going from A to B, I can figure out some area, but if I'm going from B to A, then I'm computing it backwards, and I'm going to get the opposite sign of it. So regardless of which one's bigger or smaller, A or B, it's irrelevant. If I'm reversing these numbers on the integral symbol, the interval, if you will, then it's the same as if I changed the area, the sign of the area, and computed it the other way around. Okay? That is going to come in handy when we get to something called the fundamental theorem of calculus. Sounds very, well, fundamental. But that you'll see where this comes in handy. But basically, I can compute forwards or I can compute backwards and change the sign. Okay? If we had the area from A to B and the area from B to C, and we add them together, then what we've really done is an example a lot like this. And we had 3 pieces here. We found the area from -5 to -1, -1 to 1, 1 to 5. I could have said what I'm really doing on this problem, and I'm going to back up and write on this one just a little bit. This original problem from the very beginning could have been, I'm going to put it over here on the edge, the integral from -5 to 5. You don't have to write this. You don't have to flip back through your papers. But it was the integral from -5 to 5 of the entire function, that piecewise mess, whatever it is. And then in the process of doing it, I broke it up into 3 separate pieces. So if I want to know the area of something that is broken up, it's really the same as the area of the entire thing. I just might need to break it up at some point. So the integral from A to C of f of x dx. Okay, so again, if I want to know the integral from A to B and then from B to C, then I really could just go from A to C. It might be easier to do it this way by breaking it up into pieces. It might be necessary for whatever reason. All right, we get to the next 2, which are somewhat common sense, but if I have a constant in here, k is a constant, I think that's worth writing, so k is a constant, then it's the same thing as if I just factored this k out and then computed the integral, which of course is the area, we've said that, so I can factor that out. And then the last one is pretty straightforward as well. If I am adding or subtracting more than one term, then it's the same thing as if I do the integral from A to B of f of x dx plus or minus, depending on what I'm doing, the integral from A to B of g of x. So these are some very handy properties. These, along with the integrals of odd and even functions, are great ways to simplify things.